if we are given the data wherein independent variables and dependent variables have been identified, preliminarily we will try to model the data by using multiple linear regression model, because that is very easy to do. And once we model it by multiple linear regression equation, then we will test whether the model is capable of representing the given data. And for that, we use two criteria which we have seen in last lecture. One is RMSE, root mean square error, and another is R square. If R square and RMSE fall in favor of accepting the model, fine. But if the RMSE and R square are not allowing us to accept the model, then one may think of going in for multiple non-linear regression model. That multiple non-linear regression model could be of second order, third order, or any higher order, or it could be altogether different non-linear function which is used for modeling the given data. But if one is going in for modeling the given data by non-linear regression model, he can always be advised to use artificial neural networks, because over a period of time, this model has been established to model any kind of data. And one more peculiarity of artificial neural network is it is internally complex. The model is internally complex if you look at it, but externally it has been presented in a very simple form, that is the network from form. Okay, artificial neural network are the very popular tool of data modeling. Artificial neural network is a very popular tool of data modeling, and the inspiration obviously is taken from the neural networks which we have. And the property of how this neural network work, they take the data input from maybe from various sensory organs, and this input reaches to the neurons process it and pass it to other layer of neuron. This other layer of neuron pass it to again the next layer of neuron, and in between this neuron there are some synaptic connections which are filled in with some chemical having different types of concentration. So that is enough of biology. We need to know about our neural network which exists within us. Okay, we will be taking the clues from this and directly be entering into the neural networks of our interest. Okay, whatever the data which we need to model is fed to the neurons here. As you are seeing here, the data is fed to the neurons in the input layer. That implies that there are multiple neurons in the input layer. And multiple means how many exactly? The number of neurons in the input layer are equal to the number of independent variables in your data set, right? Number of independent variables in your data set will be determining number of neurons in the input layer. Okay, those neurons are indicated, represented by circular structure. Those are also called as nodes. Okay, in neural network language, these things will be calling as neurons. So they are how many? The number of neurons is equal to number of independent variables. And then there will be number of neurons in the on the other end of the network, and those neurons will be equal to the number of outputs you are interested in, right? You may have different neural networks for different outputs, or you may combine all the outputs in one neural network. So once again, You have number of neurons in input layer equal to number of independent variable, and in output layer, this is the last layer, is called as output layer. You may have only one neuron in output layer or multiple neurons in output layer, depending upon how many outputs you are interested in and what is the policy of dealing with the outputs. If you want to deal with each output individually, then in one network you will be having only one output neuron. Otherwise, if you are interested in having a combined network for all the output, then all the output neurons will be in one output layer. In between input layer and output layer, there will be multiple layers. Those are called as hidden layers. In each of the hidden layer, it is your discretion to take number of neurons. Like in this figure, you are seeing that there are two neurons in first hidden layer and three neurons in second hidden layer. You can have multiple hidden layers. In deep neural networks, there are so many hidden layers, right? And in each of the hidden layer, you are free to decide how many neurons should be there in that hidden layer, in each of the hidden layer. Okay, like here in this neural network, you are having three in first hidden layer, you are having three neurons. In second layer also you are having three neurons. In output layer you are having two neurons. So this, now how will you know the, how will you communicate the structure of network you have designed or someone else has designed? How will be the communication regarding that network? So there is something called as topology of the network. Suppose say I have the I say that 5 slash 3 slash 2 slash 3 slash 1. What does that indicate? 5 will be, first 5 will be indicating that they are the input layer neurons. Then second 2 will be indicating they are the number 2. There are two neurons in first hidden layer. Third 3 will be indicating there are three neurons in second hidden layer. Again, there is, if there is next value 2, then that will be indicating there are two neurons in third hidden layer, and finally one indicates that there is one neuron in output layer. So the topology is written in this simple terms: 5 slash 2 slash 3 slash 2 slash 1. Okay, you may have any number of any numbers at the place of 5 slash 2 slash 3 slash 2 slash 1. Okay, that's that. Once this is given to you, then what you are supposed to do, you will be drawing 5 neurons. In this case, suppose how many are there? There are 6. So say my input layer has 6 neurons, and in the first hidden layer there are 2. Then I know what I have to do as per as the connections in between input layer and first hidden layer is concerned. From each of the neuron, what I'll be doing, I'll be connecting each of the neuron in input layer with each of the neuron in first hidden layer. Okay, like done here. And then first hidden layer is connected to every neuron in the second hidden layer. Likewise it goes. So it is enough for you to know simply the number of neurons in each of the layer. Once you know these numbers, then you can complete the network, because every neuron in previous layer is connected to every neuron in the next layer. Okay, so topology is very important term in the artificial neural network, right? So now what we need to do, what we do with this topology, once we form the neural network of the topology, we have to plan for giving the inputs to the input neuron. What we are seeing now is the feed forward backward propagation neural network. Right. So, to make you understand the neural network, what goes on in neural network, we'll be taking very simple topology. The topology, as you see here, is 2 slash 3 slash 2 slash 1. Okay, this is not the neuron. This is just the standard to compare the value of output neuron with the known value of output. Right. So with that topology 2 slash 3 slash 2 slash 1, we have drawn this neural network. Now, one thing you must understand that the neurons are to be fed with the data which ranges between 0 to 1 or minus 1 to 1. Okay. So that decision you have to take whether the data, now the data which you will be having will not be ranging between 0 to 1, but you can always map the data which you have to the values between 0 to 1. Okay. Or you can as well model, you can map the data to values which lie between minus 1 to 1. This decision you have to take right in the beginning whether my data will have to be mapped between minus 1 to 1 or 0 to 1. Okay. So right here we'll be taking that I will be mapping the data between 0 to 1 because this decision makes a difference in my processing, in my choices later on. If I decide to map my data between 0 to 1, then there is something called a sigmoidal function about which we'll be talking little later. I will be using one particular type of sigmoidal function, and if I decide to map my data between minus 1 to 1, then I will be using some other type of sigmoidal function. So we will be going with the that we will be modeling our data between 0 to 1. All right. So this is the data which is given to us. This is actually, in fact, this matrix tells to you about the data. There are only two inputs, x1 and x2. Their values are given to you here. All right. Their values are given to you here, right, and the corresponding output value is also known to you, right. Now what we do, I have for visibility sake, what as to what goes on in a neural network, I have separated x1 column, and that is happening to be the input to the first neuron, and x2 column, x2 row rather, has been written here. Okay. And that, but not directly, will be happening the input to the second neuron. And this, what is happening to the independent variable row, that is given to the output node, output neuron, not exactly output neuron, but that one neuron which we have created after the output neuron. So what we did, x1 column. Now this data, I have written 1, 2, 3, 4, like that. Means the first data which will be entering into this neuron is written first, and second data which will be entering is written second from this end. Right. So it is written in the sequence of its entry into the neuron. But this data, as I have said, that this data will not be directly entering into this neuron or this neuron. This has to be first mapped into what is called as mapped into value between 0 to 1. How to map it between value, it in value between 0 to 1? So we see here minimum value in this data is 1. So that 1 will be equivalent to 0. And maximum value here is 8. and that 8 will be equivalent to 1 in our map. So I can either get the equation of line with the coordinates 1 0 and 8 1. I can either get the equation of line, or I can directly write the thing like x1, that is the variable, that is the data which will be coming here, minus 1 divided by the difference between the smallest and largest value. 8 minus 1, that is how much? 7. That will come into denominator, just to verify whether this rule will map the data in between 0 to 1. But I keep the minimum value in place of 1. 1 minus 1, 1 minus 1 is 0, right? Divided by 7. 1 minus 1 divided by 0 divided by 7 will be giving you 0, and 8 minus 1, 8 minus 1, that is 7. 7 divided by 7 will be getting you 1, and all the values in between 1 and 8 will be giving you value greater than 0 and less than 1. That is how we map the data, given data between values 0 to 1. So this is a processor to convert this data to values between 0 to 1. Likewise, this is another processor. Here I think there is little bit of mistake. X2 minus 2, this value should have been x2 minus 2, right? Now minimum value here I am finding is how much minimum value which I'm no see, minimum value which I'm finding here is what minimum value which I'm finding. Yes. In this, even though you are seeing that the minimum value is 2 and maximum is 10, but this is not the only data. This is the segment of the data which you are seeing. But the data has actual value of x2, minimum value of x2 from the complete extent of the data is 1, and maximum value is 14. This data lies between 1 to 14, that is say given to you. So in that case, this rule will be what? X2 minus 1 divided by 14. Alright, x2 minus 1, because what you need to do, x2 is the variable which is entering into variable value which will be entering here, then minus the minimum value which you have in the data divided by difference between minimum value, maximum value and minimum value. That will translate the data which you have in between value in between 0 and 1. So once that is done, that is the value which is getting paid to this and this neuron. Like for example, this neuron will be getting its first value 0, and this will be getting its first value 2 minus 1 divided by 14, that comes 0.07. Now, what is done to the connections in between the two layers? These connections are initially fired with some random values which are called as random weights. These values which I have written on the connections are called as weights. Okay. So you may fire them with the weights anything between 0 to 1. Right. So here you are finding value 0.57, 0.83, 0.69, 0.17, 0.24 and 0.32. Likewise, the connections in between the second layer of neuron and third layer of neurons have all been fired with the random weights between 0 to 1, and here too same thing has been done. That is the process of initializing the weights, right? And not only the weights, but there is some value which you are seeing at the top of this neuron that basically should have been inside the neuron, right? Inside the neuron, all these values 0.23, 0.41, 0.83, 0.74, 0.28 should have been inside the neuron. That value is not there here on the input neurons. Okay, but that can be on the output neuron, or may not be on the output neuron, but on all the hidden neurons in the hidden layer, this value will be there, and this value is called as threshold of the neuron. Okay, that is the threshold value of the neuron. Now, having got introduced with the structure of this network, what what kind of processing goes on? Let us look into that. First thing, you have understood that the value which is mapped in between 0 to 1 enters into this neuron and this neuron as well. Now, what is done? This multiplied by 0.57, the value in this neuron multiplied by the weight connecting this neuron with this neuron, plus value in this neuron multiplied by weight connecting this neuron and this neuron. This sum of the product is added. Okay, for example, 0 into 0.57 plus 0.07 into 0.17, that is going to be 0.242, right? To make you understand this process a little bit in detail, we'll be going to next transparency. But before we go to next transparency, there is something which we need to understand before we see the things in detail. Again, in this neuron, what is going to happen? You will be finding out all the connections coming to that neuron, and you will be finding the weights on those connections, and you will be multiplying these weights by the values at the neuron which are at the tail of these connections. So 0 into 0.83 plus 0.07 into 0.24 will give you this value 0.427. Likewise, at this neuron, you will be finding that this is the weight coming to this neuron, and this is the weight coming to this neuron. So what you will be doing? You will be multiplying. You will be multiplying this by 0.69 and 0.07 by 0.32, and that will be the value here. Got it? Having got these values, now because you are doing the sum, though you are doing the sum of the product, but when you are doing the sum, there is always the possibility that the sum here exceeds 1. And in neural network, we do not allow any neuron to have value greater than 1, greater than the range in which it is to be bound. Like our neural network is to be bound in between 0 to 1 value. So what we have decided that any neuron should have value between 0 to 1. So we are not sure that this value will be between 0 to 1. It may be, it will be any value. It can be anything greater than 1 or less than 1 as well. But we will not be knowing maximum value which occurs at this neuron, which will be there at this neuron. We will not be knowing, because there could be multiple neurons in the input layer, and there will be multiple weights, and there will be some. So it could be any value because of all these things going on there. All right. But we want the value at the neuron to lie between 0 to 1, and we cannot use this kind of trick to convert the value of the neuron to lie between 0 to 1, because for using this we need to know maximum and minimum value. Here we do not know that. So what we do, we use what is called a sigmoidal function. Okay, one such sigmoidal function is 1 upon 1 plus e to the power minus n in. What is this n in? That n in is the value at the input of the neuron. Okay, at the input of the neuron, if we know that value, like for example 0.242 here we know, and we put it here, we will be getting the corresponding out value. And what is the property of this out value? It will lie between 0 to 1. It is the sigmoidal function. Minimum value written by this sigmoidal function is 0 and maximum is 1. Whatever be the value of this minus, whatever be the value of this n in means neuron in, whatever be the value, may it be 500, 5000. If it is this positive, you will find that the value will be landing on one side, or else if it is if it is positive, then it will be landing on zero side. Okay, but in no case it will be lesser than 0 or greater than 1. So this function has the property of converting any value to value between 0 to 1. All right. Now this is another sigmoidal function. This is e to the power n in minus e to the power minus n in upon a to the power n in plus e to the power minus n in. Okay, something like hyperbolic tan, right? And its property, as you are seeing here, the value of this n out, once you put the neuron input value at all these places, it will get translated to value between minus 1 to 1. All right. So there are many kinds of sigmoidal functions which will be converting the value at the neuron to lie between 0 to 1 or minus 1 to 1. Okay. So whatever be the value at the neuron, it will get converted to the proper value to lie between 0 to 1. That is the significance of sigmoidal function. Okay, so we will look little details of sigmoidal function, but before that, a short recap of what we have seen so far. This is the data. This is the data, x1 and x2. We have split it as per the neurons, and we are translating the data to lie between 0 to 1, because neurons can take the value between 0 to 1. So by this equation, or by finding the equation of line, you will get the same thing. Okay, so your data will be converted to lie between 0 to 1. Okay, here too, and that data enters. Now this data, now you to find the value at this neuron, what you will be doing, you will be finding the connections coming to that neuron, and weight on that connections multiplied by the neuron values at the tail of these connections will be giving you the neuron input for this particular neuron. And to get neuron output, you will be processing that neuron input by using a sigmoidal function. The purpose of using sigmoidal function is to make sure that the data at the neuron which progresses ahead lie between 0 to 1 in this case, or it lies between minus 1 to 1 in this case. All right. And what is this thing we are doing on this side? Right here, this complete y set is taken here, and this y set, again about y set, this is the segment of the data, and from the complete data it is known to me that minimum value of y is 1 and maximum is 19. So therefore the translator, the transformer which will be transforming this data between 0 to 1 has been constructed here. Its maximum value is 20, sorry. Okay, so y minus minimum value upon maximum value minus minimum value will be ensuring that any value in this data will be converted to the between 0 to lie between 0 to 1. Okay, this data, when I am passing first data to this neuron, the first data from this segment will be passed to the target neuron. This is not output neuron. This is the target neuron. This is the value in which you are interested in. What will be that value? 2.24 minus 1 divided by 90 approximately comes equal to 0.065. All right. Now, having understood this, we will be checking little more properties of this sigmoidal function. Okay, there is one denominator to this NIN that is called as Q, and that is referred as temperature. Okay, like written here, net out or N out is equal to 1 minus um, mm, 1 minus 1 upon um, uh, one minus this one minus is not that essential here. 1 upon 1 plus e to the power minus net in or n in by q. This is something new here. Okay, q we have put in a denominator. Okay, what is the property of that q? Soon I change the value of q from zero point 0.5 to 10. You see what happens to that sigmoidal curve. Lesser this value, it will be very much insensitive to the changes in and in, because you are seeing that that is too much tape. Okay, that its value is probably changing between minus something like point minus 1 to plus 1, or might be minus zero point 0.5 to zero point 0.5 for any changes in the value of that is to say, the changes in the net in value are properly reflected by sigmoidal function if net in value lies between minus zero point 0.5 to zero point 0.5. For example, as I go on increasing Q, the span of sensitivity goes on increasing. Like you are seeing here, I have made Q to 1. So this is the second curve. Q I have made 1.5. This is the third curve. Then 2. Then 3. Then 4. And then I have made it directly 10. This Q, which is called as temperature, I have made it 10. And you are seeing the sensitivity of the sigmoidal function has increased. Okay, now it is converting to meaningful net out from the net in, which is varying between something like 50 to 50. Okay, the values of net in which lie between 50 to minus 50 to plus 50 are properly mapped in between that range. So you may not be always using sigmoidal function in its original form like given here. You may divide this neural network in by q, so that you get the more sensitive sigmoidal function. Okay, if it is vertical, then we will have the problems in training of this neural network. So if it is spread to greater length, if it is spread like this, then it would exhibit certain benefits in training. Okay, so this thing, what is the role of q, effect of temperature q on net out, that we have seen here. Okay, so far we have seen that to the neurons, the data in which lie between 0 to 1 enters, right? Then from this data and the weights connecting to the next layer neuron, you get the value at each of the neuron in the next layer, that is to be processed by sigmoidal function. Okay, so sigmoidal function details we have seen. Now we will be seeing the processing of the data, forward processing of the data. Just right here you see that 1 2 1 2 has been translated to 0 and 0.071, right? Here I am trying to show the process by matrix multiplication. right? This network is indicated by matrix. At least this part is indicated by the matrix. So point 0 and point 0.07, and there is one more value in the last column, that is 1. What is the role of this one, that we'll be seeing soon, right? Mm, the- so this is the neuron. This is indicating the values of the neuron, values at the neuron which are inputting, which are in the there in the concerned layer, like 0 and point 0.07. Okay, one value I'll be talking about it soon. And this matrix is the weight matrix. Okay, here you see that this is I1 and this is I2, and this I'll be calling as H11, H12 and H13. That is, in the first hidden layer, first neuron, H12 stands for second neuron in first hidden layer, and H13 stands for third neuron in first hidden layer. So here I1 H11, you are seeing 0.57 value that is written here. I1 H12 0.83, I1 H13 0.69, likewise 0.17, 0.24 and 0.32 are respectively the weights between I2 to I2 to H11, I2 to H12 and I2 to H13. And lastly, these are the threshold values. Okay, 0.23 is the threshold of first neuron, 0.41 is the threshold of second neuron, and 0.83 is the threshold of third neuron. Now, what we do as a matrix multiplication, 0 into this weight plus 0.71 into this weight plus 1 into threshold. That is what we are doing. 0 into 0.57, 0.071 into 0.17 plus this threshold, that is simply represented here. Okay, that will be giving you 0.242 value here. This 0.242 value is coming after adding this threshold. Likewise, this multiplied by H12. Okay, all the weights coming to H12 plus the threshold will be giving you the value at this neuron, that is 0.427. Likewise, this multiplied by the third column, in the third column basically indicates all the weights coming to that third neuron, and the last value here is indicating to you the threshold. Last value is the threshold value. So that is how you got the values, net input values, or n in values, I may say, n in values 0.242, 0.477 and 0.853 are the values which I have obtained. Now these values, all these three values have been processed by sigmoidal function. Okay, that is 1 upon 1 plus e to the power minus n in. Okay, minus ni in. Okay, you may use or may not use the temperature like term, that is up to you. This neural network gives you various things. There are various things in your control, like from number of hidden layers, number of neurons in each of the hidden layer, what is the sigmoidal function you should be using. In the sigmoidal function also you are free to choose the temperature term. Okay, so right here I am using temperature as one itself, so I am getting this value. Now these values will be the input to this layer. Now 0.560, 0.605, 0.701 and lastly 1 that I forgot to put in a bracket. The 1 is still there. Okay, so what you will be doing now, just check here. Point, you will be having again the matrix of the weights between all these neurons and all this. Okay, the latter layer will be giving you the number of columns. Like in latter layer you have two neurons, so there will be two columns, and in the preceding layer there are three neurons, so there will be three rows plus one row for threshold, right? And here the weights 0.75, 0.89 and 0.26 are written here, and 0.74 is the threshold of that neuron. And in the second column H22, all the weights coming to this neuron 0.13, 0.89 and 0.48, and plus the threshold 0.28. Now all these neurons, neuron out, which are coming from here to here, plus this one value, this matrix multiplication will be giving you the values as these two neurons, 1.88 and 1.228. Again, those are processed by sigmoidal function, and you get these values. Now these values again will be coming as the at the input, and you will be having again the matrix of the weights. As I said, it will be having only one column because there is only one neuron in output layer. Okay, so one column, and there will be two rows. There could have been three rows had we considered threshold here as well, but we are not considering any threshold here. You may or may not consider threshold here. Okay, so anyway, so what is happening? There are two rows, and in the first row 0.35, in second row 0.63. This multiplied by this will be giving you only one value, that is 0.79. That is n in, net in, and by processing it after the sigmoidal function it will be 0.688. Okay, so this matrix type of thing will make the calculation easy in understanding. Now what happens, the process won't stop here. This is just first data processed. Okay, and I have got value 0.688, whereas I know that that value should have been 0.605. So there is an error. Okay, there is an error here. That error is 0.688 minus 0.605, right? That error just is kept in memory. Now what will happen? This second data, after getting mapped, this 2 and 4 after getting mapped will be the input to this neuron, and this values will then be forward processed in the forward pass till they reach here, and the error, square of the error once again will be kept in memory or added to previous square of the error. Then the third data will be mapped between 0 to 1, and that will be processed by the forward process. And again, here again the third data mapped value will be coming, and you will be getting the error. You will be squaring the error, right? You will be squaring the error and adding that error, squared error, to previously accumulated squared error. Okay, this way all the data will be processed in the forward pass, and you finally will be getting squared error. See, in what way I have written the squared error? 1 by 2 into bracket t minus y square, where t is the target output corresponding to input. Okay, target output corresponding to input, and y is the actual output of the output neuron, actual output. Okay, t minus y is the difference between what you want and what you get. Okay, square. Then why I am multiplying it by why I am multiplying it by 1 by 2? Okay, I may or may not multiply, but that gives you some differentiation advantages. If I different later on, you will be required to differentiate error. with respect to y or any something. So when I differentiate, say this 2 will come into multiply to this 1 by 2, and they will cancel each other, giving you the simple output. That's why 1 by 2 is planned. Okay, just for that. Okay, to cancel the exponent when differentiating. Okay, this was all the feed forward process. So after understanding this feed forward process, we will have to take a special lecture on backward propagation. Now what is happening in this feed forward process, that I have randomly initialized this matrix, this weights by random numbers, right, and random threshold values. Now, whole of my target here is to get this value equal to this value. I want to get the value which I am getting here equal to this value. Okay, but this, for getting this and this equal, I have to keep on correcting these weights and the thresholds. The value which is coming here is all the way function of the weights and the threshold. If I keep on correcting these values by a iterative process, then one time will come when the output which I get here, output of this neuron which I get here, will be equal to or very close to target output. I want to reach to that point, and the process of correcting this weight is called as backward propagation. Okay, so far what we have seen was forward propagation. Now we'll be seeing backward propagation. That is the method of correcting the weights and the threshold. And what for we want to correct it? For getting the output of the neuron, output neuron equal to target neuron, right? So here we will stop, and then after understanding this lecture thoroughly, you go to next lecture. Thank you.